today's discussion is going to be about writing chemical formulas, how to represent chemical formulas, and then being able to name and chemical compounds or write chemical formulas based on the name. So it really is important. And then next time we'll talk about writing the structure of compounds and understanding their properties. Okay, we're talking about ionic compounds. Okay, I think you guys can see that. And remember that back in chapter 3, we talk about matter as well as energy, and matter can be separated in terms of mixtures and pure substances. We're going to be concentrating right here on compounds, okay? And in terms of the compounds, we have 3 types, and it has to do with how the atoms bond to each other. When the atoms bond to each other, and you guys know this because the electrons are responsible for, it's the outermost electrons that are responsible for tying in atoms together. Okay, and you'll see that here. When the electrons are shared, it's called covalence. When it's not shared equally, okay, but it's pulled more towards one atom, it's called polar covalent. And when the electrons are transferred completely, we call it ionic. So these are the 3 types of compounds we have in nature. For an ionic compound, we name that differently from these guys right here. And that's what this discussion is about. It's about naming compounds, okay? So these are examples of compounds, and the compounds can either be covalent. Covalent means the electrons between 2 atoms are shared. Sometimes they're not shared equally. Sometimes one atom is going to be stingier than the other. And so it's called a polar covalent. Polar just means that it's pulled to one side versus the other. And then the other one's ionic. Ionic simply means that the electrons of one atom goes to the other atom because it has a greater tendency to attract that electron. So what you form are ions. The one that loses electrons are now going to have deficient amount of electrons, so there's more protons than electrons, so it's called a positive ion. It's called a cation. The one that gains electrons is going to have more electrons than protons. Those are the only ones that are charged, and so it's called a cation. Okay, it's called a cation. And then the 2 anion and cation are going to be attracted because opposite attracts, and we call those ionic compounds because they're formed by ions. Okay, so that's the category of compounds that we're going to be taking a look at. Okay, we're going to be taking a look at compounds, and this is again how we classify them. This is electron transfer. When electron goes from one species to the other, one atom to the other, and this is electron sharing, but sometimes it's not sharing equally. Sometimes it's sharing because one atom is stingier than the others. And when that happens, then we have something called a polar covalent compound. Okay, a polar covalent compound. So go ahead and show you that. Okay, and then this is mutually sharing. And then this, of course, is going to be unequal sharing of the electrons, unequal sharing of the electrons. So let's take a look at how we represent compounds. And you guys can watch the movie, but I'm just going to go through this because this talk usually takes 2 lectures. So the way we represent compounds is the name. Like we know water as water, or methane or ammonia, things like that. Okay, so just giving the name tells the person who understands a little bit about chemistry what chemical you're speaking of. Okay, and then there's the formula, and the formula tells you the makeup of that particular compound. Like water's H2O, 2 hydrogens and 1 oxygen. Methane is CH4. Glucose is C6H12O6. Okay, so that's the chemical formula. Then there's the molecular formula, and molecular formulas are only for chemicals in which the electrons are shared between two atoms. Sometimes they're not equally shared, but they're shared. So molecular compounds are ones in which the atoms involved are non-metallic, non-metals. Okay, so carbon and oxygen, phosphorus and oxygen, or hydrogen and chlorine. Okay, these are molecular compounds. And why they're called molecular? Because they exist in terms of a special entity, like what we have right here. This is water. It's a molecular compound. That's versus an ionic compound. And ionic compounds are formed because the ions are formed. That's because there's an electron transfer. And then the ions, the positive and negative, are attracted through electrostatic interaction. Okay. We have the structural formula, and that's just a way of representing these chemicals through the elements that make them up, or the a figure that represents their composition. Okay, this is the space filling model. This is a ball and stick, and then like these as well. And you guys are going to learn how to do that, to do this in this particular chapter. The empirical formula takes the formula of a compound and break it down to its simplest ratio. Something like this right here is glucose, C6H12O6. But when we analyze glucose, we can't analyze it for 6 carbon, 12 hydrogens, and 6 oxygen. Usually our analysis will only tell us the ratio by which the carbon, hydrogen, and oxygen exists, that it's a 1:2 to 1 ratio. And that's the empirical. The empirical tells you the lowest ratio by which those atoms exist for a compound. Okay, water is H2O. So the chemical formula of water is also the empirical formula. Hydrogen peroxide is H2O2. So the empirical formula for hydrogen peroxide is just HO. There's the lowest ratio by which that particular species exists. And why do we have the empirical formula? Because when we analyze compounds, usually we can only analyze the ratio by which these elements exist for a compound. Okay, and then we have to do further experiments to kind of figure out what the true formula happens to be. So the empirical formula is the lowest ratio of atoms in a substance. And then there's a formula unit. And the formula unit, okay, is like the empirical formula, but it's generally for ionic compounds. It's generally for ionic compounds. And you might ask yourself, why are some chemicals called ionic compounds and the other ones just called compounds? Ionic compounds originates from the fact that the chemical that they represent comes from ions. And they come from ions because the electrons in one atom are transferred to the electrons of another atom. And so what you have are ions, okay? Like, for example, you know salt. Salt is NaCl. That's an ionic compound. Sodium has 1 electron in its valence shell, and you know that based on the periodic table. Chlorine has 7 electrons in its valence shell. That's the outermost shell. All atoms want to have the same electron configuration as a noble gas. When they do that, then it becomes somewhat metastable. So when sodium gives up its 1 electron, then it has the same number of electrons as neon, and it becomes stable in that fashion. When chlorine picks up 1 electron, then it has the same number of electrons as argon. Okay, it's still chlorine, but the number of electrons has changed because of that transfer. One now is positive, the other one is negative, and that attraction for each other makes it an ionic compound. Okay, it's an ionic compound. And the lowest ratio by which those particular chemical exist, ionic compounds, are called the formula unit. Okay. So again, I'm just trying to introduce you to the vocabulary that we use, because in the later chapters, I'm just going to say this ionic salt and you should already know that, oh, okay, it's a chemical in which there's a metal and a non-metal, and the metal gives up its electrons to form ions. Okay, so there's two main types, like I said, and one of the type is, just make sure that there is no covalent. And covalent, the co means with, valence means the outermost shell. So covalent means that the outermost electrons are being shared between two atoms. Okay, that's what covalent means. And sometimes they're shared equally, sometimes they're not shared equally. It's sort of drawn to the more stingier atom. And then there's something called ionic. And the reason why it's called ionic is because when the compounds form, they combine because one is positive and one is negative. They combine because these are ions. Remember that ions are atoms that are charged. And the reason why they're charged is because the protons and the electrons are not the same. Okay, the protons and electrons are not the same. And so if you have more protons and electrons, then you are positively charged. We call that a cation. If you have more electrons than protons, then it's negatively charged. We call that an anion. When one element gives up its electron to the other, it's going to have a deficiency of electrons. It's going to be positive. It's going to be a cation. So by an element giving up an electron, it now becomes positively charged. It becomes a cation. That other element now picks up that electron and it becomes negatively charged. We call that an anion, like an ant. Okay, looks like a minus. And ions are negatively charged because it has more electrons, which are negatively charged, than protons. Now, these compounds, because they're oppositely charged, are going to be attracted to each other. Opposites attract. And so that's what makes an ionic compound. It's because you form a cation, you form an anion, and now they are attracted to each other through what we call Coulombic interaction. Coulombic just means charge. Okay, so that's essentially the two types of compounds that we will see, and we will take a look at these compounds, more so this than this one and this one in this particular section, covalent and ionic compounds. Okay, you have to know something about why these compounds form. The reason why compounds form is because if you look at the periodic table, you'll see that at the very right corner, there's these group of elements called the noble gas. The reason why they're called the noble gas is because they tend to be inert. That is, they tend not to be chemically reactive. They're totally satisfied with just being isolated. And why? Because the outermost shell is filled with electrons that is just the right amount. It doesn't need any more. It doesn't need to get rid of any more. Everything's gonna filled. And you guys learned that back in chapter 4 when you did electron configuration. Okay, when all the shells are filled, then that satisfies the atom, and you get something called a noble gas configuration. It may not be a noble gas because the protons determine the identity of the atom, but at least the electron shell has the same number of electrons as a noble gas, and that gives it added stability. So the octet rule simply says that atoms are going to give up electrons or accept electrons or share electrons until they have the same number of electrons as the noble gas. And that usually is in its outermost shell 8. That's why it's called the octet rule. Okay, so that's how compounds form, when they can negotiate with each other so that each individual atom is satisfied and will have a noble gas electron configuration. It will have the same number of electrons as a noble gas, so closest noble gas. It doesn't change to a noble gas, however, okay? Because in order to change to a noble gas, you have to change the number of protons. The number of protons dictate the identity, but if it can have the same number of electrons in its outermost shell as a noble gas, then it gains added stability. Okay, chemistry is sort of weird in that sense, and I know that you guys are learning these things and you have all these rules, but the atoms, when you form these compounds, they just want to be happy, and they want to be happy by the electrons are what speaks to each other in compounds. They're going to be shared between atoms. They're going to be transferred. They're going to be accepted or released, so that it has the same number of electrons as a noble gas. Now, there are always exceptions to those rules. Okay, there's always exceptions, but that's the general trend. Okay, that's the general trend. So, like I said, ionic compounds, the electrons are transferred. Why? Because maybe you have an element that has 2 valence electrons. If it can get rid of the 2 outermost electrons, the inner core now has the same number of electrons as a noble gas. Maybe you have chlorine, it's got 7 valence electrons in its outermost shell. If it can pick up 1 more, it has 8, and 8 is the magic number. If it can have 8 in its outermost shell, it has the same number of electrons as a noble gas. And that's how chemistry is made. When atoms react with each other, it's to ensure that the electron count in the outermost shells are stable. And when they become stable, then they will form bonds. They will form bonds. And this is an example right here of what I mean. Sodium has 1 electron in its valence shell. Okay, and you know that because sodium is in the 1A family in the periodic table. If you have a periodic table, there's a periodic table, okay, and you know how many electrons are in the outermost shell on the periodic table by just knowing how to read the periodic table. This is the 1A family. This is the 1A family. Since it's in the 1A family, it's got right here, it's got 1 electron in its outermost shell, okay? There's going to be an inner core, but the outermost shell is where chemistry occurs. This is the 2A family. It's going to have 2 electrons in its outermost shell. This is the 7A family. It's got 7 electrons in its outermost shell. So those are the parts of the atom that is responsible for chemistry. It is those parts that are going to mingle with each other in a chemical reaction. Okay, so that's why it's important to understand electron configuration. Why? Because when you understand electron configuration, then you understand why these electrons are going to exchange from one atom to the other, why one wants to give up an electron, why one wants to accept an electron, why they want to share electrons, because it's the electrons that dictates the chemistry. Okay, all these elements down here have 1 electron in its outermost shell. It's only the outermost shell of an atom that is responsible for chemistry, because those are the parts of the atom that makes first contact. Okay, so when it gets rid of its outermost shell, rubidium now has the same number of electrons as krypton. It goes from 37 electrons to 36 electrons. It gains added stability because all the electrons are paired. Okay, atoms want to have the same number of electrons as the noble gas, and what they will do is they will get rid of their electrons, they will accept electrons, or they will share electrons until they have the same number of electrons as a noble gas. There are exceptions out there, okay, but that's the general trend. These elements here all have 2. These elements right here all have 3, 4, 5, 6. Now these elements here, okay, they're a little bit more complicated because they start filling the d orbitals. And you guys should know that because you covered chapter 4, electron configuration. But that's where we're going with this chapter. In order for compounds to form, the outermost electrons have to communicate with each other, and they will either be transferred from one element to the other, so that they have, by getting rid of that electron, it has the same number of electrons as the noble gas. By accepting the electrons, it has the same number of electrons as the noble gas. Remember, these are the elements that have noble gas electron configuration. It doesn't become a noble gas. The protons dictate that, but the number of electrons now are going to have the same number of electrons as the noble gas, the closest noble gas, and that gives it added stability. So it's going to transfer, it's going to accept, or it's going to share those electrons so that you have the same number of electrons as a noble gas. That's the key to chemistry. That's the key to understanding how compounds come together. And then when you can write the formula, you will be able to name the compound. But you got to get the formula correct first. Okay, we're talking about these. And again, electron transfer, the sodium will get rid of electrons. It now has a neon electron configuration. That is, it has the same number of electrons as a neon. Fluorine now picks up an electron. Okay, and by picking up an electron, it will now have the same number of electrons. It doesn't become argon, but it has the same number of electrons as argon, and now they have a full packed shell, and it's stable that way. But one is positive because it lost an electron, the other is negative because it gained an electron, and then the positive and negative are attracted because opposite attract, and that's what we make. That's how we make ionic compounds. Ionic means ions. Ions means charge. Ionic compounds are charge fragments that are attracted together. Okay. Then you have covalent compounds. Covalent compounds, they can't really get rid of electrons because covalent compounds are made by nonmetals. Nonmetals don't want to give up electrons. Metals do want to give up electrons. Why? Because by giving up electrons, it has the same number of electrons as the noble gas. Nonmetals, however, too much work to give up all its electrons. Okay, it's on the right side of the periodic table. It's not going to give up 5 electrons, not going to give up 6 electrons. What it'll do is it rather pick up electrons. But when you have 2 atoms, like 2 fluorines coming together, one atom is not going to give up 7 electrons to satisfy the other. It's too much sacrifice. So what do? They mutually agree to share one of their electrons apiece. And when they do that, when they mutually share their electrons, okay, so this is the picture that you see. These are the 7 electrons from one fluorine. These are the 7 electrons from the other fluorine. But when they form a compound, what happens is that the electrons that is shared now counts for both sides. This fluorine now will have, in this particular case, 8 electrons in its outermost shell because it's borrowing from a neighbor. And then this fluorine over here will have 8 electrons in its outermost shell because it's borrowing. You can count those electrons that are shared between the atoms for both sides of the elements that are sharing those electrons. Okay, and this occurs for nonmetals. Why nonmetals? Because nonmetals are going to be composed of elements that don't want to give up electrons. Okay, so rather than give up electrons, it wants to accept electrons, but the other partner doesn't want to give up electrons, they agree to mutually share. And the key here is that when they agree to mutually share, then the electrons that's being contributed from the other atom counts for the atom that is attracting it, and that completes what we call the octet rule. It satisfies the fact that now this element, quote, quote, has 8 electrons in its outermost shell. It has the same number of electrons as a noble gas, essentially. And that's how chemistry occurs. That's how chemistry occurs. So that's how covalent compounds are formed. Okay. So again, this is just a pictorial of what's going on. The sodium will give up the electron to chlorine. It now has 1 electron less, but it has the same number of electrons as the noble gas. Chlorine doesn't get rid of 7, it picks up 1 more. And then by picking up 1 more, it has the same number of electrons as the noble gas. Then these atoms, because they're oppositely charged, they're going to be attracted to each other. And that's where ionic compounds form, because they're ions that are mutually attracted together. That's why it's called ionic compounds. Ions that make the compounds, okay? Remember that a charged atom is called an ion, whether it's positive or negative. A charged atom is called an ion. So Ionic compounds are composed of elements that gave up or accept electrons, and they are charged. That's why they're called ionic compounds. So that's what we have right here. But you got to remember, the positive sodium and the negative chlorides are charged. So it's not going to pick, like if there was a sodium atom isolated, it's not going to look for one chlorine and says, I pick you to be my partner. It's actually going to be attracted to all the negative particles, all the negative chlorides out there. And then the chlorides are going to be attracted to all the positive ions out there. And so it's not a one-on-one ratio. It actually is a lattice. It's a lattice. It's an alternation between a positive, negative, positive, negative. But when you look at the lowest ratio, it's 1 sodium to 1 chloride. Okay. That's what ionic means. It means that this positive is going to be surrounded by as many negative as possible. The negative is going to be surrounded as many positive as possible. And they form this lattice or three-dimensional matrix. And that's what we have. But this only occurs now for ionic compounds. Ionic compounds exist in this three-dimensional array. Covalent compounds where the electrons are shared, like F2, they don't form this matrix, okay? You could isolate F2 or H2O, but NaCl, you can't isolate that. You can't isolate a single NaCl because when you take one crystal of salt, it's actually a three-dimensional array of sodium chloride in this structure. So you have to understand why that's the case, as opposed to like water where there's a single molecule. This is basically a ionic compound. Ionic compound exists in three-dimensional matrix. So here's sodium chloride. It's an example.
This will be our example ionic compound. NaCl does not exist as a single unit, like a molecule. This goes for all ionic compounds. So this would not be a valid way to represent sodium chloride. And like any ionic compound in the solid state, sodium chloride exists as a crystal. So a very, 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 very tiny crystal would look like this with alternating sodium and chloride. And a little bit of a different view. The formula unit is NaCl. But if we look inside the crystal, the sodium and chloride ions are actually bonded to 6 oppositely charged neighbors. So if we shrink the ions, we can take a better look inside. And it's a little bit hard to see. So what we're going to do is take a look at a particular chloride ion, that one right there.
Chlorides are always bigger.
Question, how many sodium ions is the chloride ion close enough to bond with? Start with the head-on view first. And as we change the perspective, you can see there are exactly 6 sodium ions that the chloride ions is equidistant and can bond to. If we ask the same question of sodium, how many chloride ions can it bond to? Well, again, there are 6 chloride ions that it's equidistant to, and therefore the sodium ion also bonds to 6 chloride ions. So as you go throughout the crystal, you can see that is always the case. Because each sodium is bonded to more than 1 chloride ion, and each chloride ion is bonded to more than 1 sodium ion, then you can think of all the ions in the whole crystal part of one single bonded unit. And the crystal below would be Na32Cl32. So you can imagine that would be very impractical given the enormous numbers of ions in a crystal large enough to see with our eyes. So only the ratio of ions is given, and that would be its empirical formula. But we call the empirical formula of an ionic compound the formula unit. And sodium chloride is the formula unit for the sodium chloride crystal. And it is the smallest whole number ratio of sodium and chloride ions in the crystal. So all formula units are the smallest whole number ratio of the ions in the crystal. That goes for all formula units. Here's another example, calcium fluoride. You've got 1 calcium for every 2 fluorides. Calcium is 2+, the fluoride is 1-. Okay. It has a slightly different crystal structure to account for, rather than the 1-to-1 ratio of sodium chloride, you have a 1-to-2 ratio of calcium fluoride. And if we shrink the atoms to take a better look, and see how the calcium is connected to the fluorides, you can see that each calcium has 8 nearest fluoride neighbors, and so it is equally bonded to those 8 fluoride neighbors. And if we look at the fluorine, each fluoride has 4 closest calcium neighbors. And again, like sodium chloride, the whole crystal acts as one single bonded unit, and so we need to express the formula as the lowest whole number ratio being CaF2. So what about molecules? How are they different? Let's take a look at water. We've got the space filling model on the left, ball and stick model on the right. It's covalently bonded hydrogen and oxygen. And a collection of water molecules is just that, a collection of individual units of H2O that are covalently bonded single units of 2 hydrogens and 1 oxygen. They're not connected to each other except by weak forces. And so large amounts of H2O, any interaction between the water molecules due to weak forces, the molecules behave, they still behave as individual units, not one large bonded unit as in an ionic crystal.
So that should give you an idea of how we classify these compounds. They're either sharing electrons, and so we say that they are molecular, polar covalent, or covalent. They're sharing, or there's a transfer of electrons, and we call it ionic. So there's 3 types, really. 2 of these are going to be sharing electrons. 1 of those 2 not sharing electrons equally. Okay, and then the 3rd type is complete electron transfer. So let's take a look at this again. I think we've already talked about this one right here. Why is this important? Because when you take a look at this, periodic table, this thing is color coded. The reason why it's color coded is because I want to make it easier for you in order to figure out what type of compound do I have. Do I have one in which electrons are shared, one in which electrons are transferred? Do I have an ionic compound, or do I have covalent compound? Covalent compounds are where the elements that are making the compounds are sharing the electrons. Ionic compounds are those in which the elements that makes the compounds transfer its electrons to the other. Okay, so they are formed from ions. Covalent means co with the valence electrons. And so, again, it's important to be able to read the periodic table. Why? Because that's the basis by which you know how to name these things. So, like I said, the ones in yellow here, the elements in yellow here, okay, are the elements in which they are going to transfer its electrons. These electrons in the 2A, beryllium, magnesium, it has 2 valence electrons. The ones in yellow are the elements in which it has a specific number of electrons that it wants to give up. The 1A, hydrogen, lithium, sodium, they have 1 electrons to give up. Beryllium, magnesium, calcium have 2 electrons to give up. Aluminum has 3 electrons to give up. Zinc has 2, as well as cadmium, and silver has 1. Okay, so the ones in yellow are the elements in which you know exactly how many electrons it's going to give up. The ones in the middle here, okay, scandium, titanium, vanadium, those are elements in which you don't know what they're going to do. They're called the transition metals. And generally they'll give up electrons, but you don't know how many electrons they want to give up. All metals want to give up electrons. And where are the metals in the periodic table? The metals in the periodic table are to the left of this line right here. I don't know why my pen's not working, but just bear with me. If you look at boron, sodium, arsenic, that's the border between the metals and the non-metals, and metals generally give up electrons. Elements like in nitrogen, oxygen, the one in pink here, they tend to hold on to their electrons. And so when they hold on to their electrons, they're not going to form ionic compounds. They're actually going to form compounds in which electrons are shared. Okay, so this particular table is really important in order to understand how compounds are formed. Okay, and that's the basis by which we're going to have our discussion here in writing chemical formulas and naming chemical formulas. So first thing that you need to know is what are some of the charge for these compounds? And we call that common charge oxidation state. Oxidation just means that it's going to have a charge. If an element gives up electrons, it's now going to have more protons than electrons. So we call that a cation. And so its oxidation state is plus. Okay, like sodium. Sodium has 1 electron in its valence shell. How do you know that? Because sodium is right here. Okay, sodium's right number 11 in this periodic table. It's in the 1A family. By giving up 1 electron, it now has the same number of electrons as neon. Okay, it doesn't become neon, but it has the same number of electrons as neon. Neon has 10 electrons, but so it's still a sodium atom, so it has 11 protons. 11 protons and 10 electrons, that gives it a net charge of +1. That's how you know it's +1. Okay, if you take a look at the element next to it, magnesium. Magnesium has 12 electrons total. That's from the atomic number. But the number of electrons in its outermost shell is 2. How do you know that? Look at the very top. It says 2A. That's the number of valence electron. Now, it wants to have the same number of electrons as the noble gas. The closest noble gas is going to be neon. It wants to have 10 electrons in its outermost shell. How does it do that? It gets rid of the 2 electrons. And now it still has 12 protons because magnesium has 12 protons. But by giving up the 2 electrons, it now has 10 electrons. So the net charge of magnesium when it becomes an ion is +2. So that's how you can tell what charge an atom will have by giving up electrons. And all the elements in the yellow, you can see right below their symbol, you see the common charge. It's going to have a fixed charge. It's going to have a prescribed number of electrons that it will give up. The ones in 1A will always give up 1. The ones in 2A, beryllium, magnesium, calcium, will always give up 2. Aluminum will give up 3. Zinc and cadmium will give up 2, and silver will give up 1. There's no doubt about that. There's no exception to those rules. On the other hand, if you take a look at the middle of the periodic table, which we call the transition metals, sometimes this metal will give up 1, sometimes they'll give up 3, sometimes they'll give up 4. You don't know. So you have to determine or tell the audience how many electrons it's going to give up by its name. Then the electrons over here in pink, right here in pink, they don't want to give up electrons. They want to accept electrons, but because it's easier for these elements to gain electrons to have the same number of electrons as the noble gas. If you take a look at the fluorine, number 9, or chlorine or bromine, they have 7 electrons in its outermost shell. Why give up 7 when you can pick up 1 and have the same number of electrons as a noble gas? If you take a look at oxygen, sulfur, and selenium, that's the next elements over. Why give up 6 when you can pick up 2? That's why you see at the very bottom of each symbol what their common charge is. Okay, nitrogen's common charge is -3, but there are some compounds in which nitrogen's -1, or some compounds in which nitrogen is -4. But you don't have to worry about that. Just know the common charge. And that means that you have to be able to read the periodic table. Okay, and the way to read the periodic table is remember the cardinal rule. Atoms will give up, accept, or share so that they have the same number of electrons as the closest noble gas. Closest noble gas. And what does the noble gas have? The noble gas, which is this 8A family, helium, neon, argon, have a complete set of electrons in its outermost shell. So again, know how to read the periodic table. The ones in yellow are generally have fixed charge. The one in, I don't know, greenish blue, they're going to have variable charge. And then the one in pink, they're negative anions. Okay, they're negative ions. And together, when they come together, they make compounds. They make compounds. So here's what I mean. These are the cations with fixed charge. These are the anions with those charges. Fluorine will always have one, chlorine -1, bromine -1. Why? Because they have 7 electrons in its valence shell. By picking up one more, it has the same number of electrons as a noble gas. These are the transition metals. They have variable charge. You have to tell the audience how many electrons it gives up. Okay. So oxidation state is basically the charge of an atom when it loses or gains electrons. Okay, it's the charge of an atom when it loses or gains electrons. So the 1A family will always lose 1 electron. It's going to have a +1 charge. Okay, the 2A family, it's going to lose 2 electrons. That's going to be a +2 charge because it loses 2 electrons. It now has 2 more protons than electrons. The 3A boron's the only one that will do this. If you take a look at the anions, that's the one on the right part of the periodic table. The 7A family, that's fluorine, chlorine, bromine, they want to pick up 1 electron. So it has 1 more electron. It has a -1 charge. The oxygen, sulfur family, it has 6 electrons in its outermost shell. By picking up 2 more, it'll have the same number of electrons as a noble gas. It has a -2 charge. So you guys know how to determine charge by something called the octet rule. The elements want to give up or gain or share until it has 8 electrons in its outermost shell. Okay, and these are common ones. Okay, these are common ones, but sometimes you have a little bit of complication. Sometimes you have groups of atoms, okay, and these are called polyatomic. Poly meaning many, atomic, and they are charged group of atoms, and they satisfy the octet rule as well, but these are polyatomic ions, and you just have to know these polyatomic ions in terms of their formula and their charge. Okay. The neat thing about your course is that generally the exams are going to be open book. You can use your book. So you don't have to memorize it, but find a good source. So if you need to find these ions, you can refer to that source. Okay. Now let's take a look at how ionic compounds form. Okay. Potassium. If you look at the periodic table, you see that potassium right here, okay, potassium is right here, number 19. It's got 1 electron in its valence shell. That's why it's +1. Okay, if you take a look at, unfortunately, I have to do this, fluorine. Fluorine is in the 7A family. It's got 7 electron in its valence shell. If it picks up 1 more, then it's got a -1. Well, guess what? The +1 and the -1 of potassium and fluorines are going to work together to be attracted. And so the formula for the ionic compound potassium fluoride is Kf. It's a 1-to-1 ratio. Okay. Let's take a look at another example. Let's take a look at another example. Let's see. Well, before we do that, make sure that when you write ionic compound, you know what the common charge of the metal is. And again, you just have to look at the periodic table. You know what the common charge of the anion is. You can look at the periodic table. And the key to form ionic compound is that when the elements meet together, it has to be electrically neutral. The positive charge and the negative charge of the 2 species coming together have to be equal. So it was easy to see in potassium and fluorine. Potassium, by giving up 1 electron, is +1. Fluorine, by gaining that 1 electron, is -1. So they come together and become potassium fluoride, 1-to-1. But sometimes it's not that easy. Okay, sometimes it's not that easy. Let's say we have barium. If you look at barium in the periodic table, it's in the 2A family. So it wants to give up 2 electrons. And let's say it wants to bond with nitrogen. If you look at nitrogen in the periodic table, you'll see that it wants to gain 3 electrons. It's -3. So how does an atom that wants to give up 2 combine with an atom that wants to pick up 3? Well, you need something called ratios. It takes 3 bariums to give up a total of 6 electrons to satisfy 2 nitrogens, in which each nitrogen wants 3 electrons apiece. By having that ratio, 3 bariums to 2 nitrogens, then the number of electrons exchanged are equal. There is no electrons left over. So the quickest way to do that is the Criss-Cross trick. You know that barium, by giving up 2 electrons, again, it wants to have the same number of electrons as the noble gas. It's +2. Nitrogen wants to gain electrons, same number of electrons as the noble gas. If you do the Criss-Cross trick, where you take 3 and make it the subscript of barium, and you take 2 and you make it the subscript of nitrogen, now you have the correct formula, Ba3N2. It's called the Criss-Cross trick. If you have 3 barium giving up 2 electrons apiece, that's 6 electrons. If you have 2 nitrogens gaining 3 electrons apiece, that's 3 electrons. That's the formula for barium nitride. It's the Criss-Cross method, okay? Let's take a look at another example. Aluminum is +3. How do you know? Look at the periodic table. Okay, look at the periodic table. Aluminum has 3 valence electron. It wants to give up 3 electrons. Sulfur, it's -2. How do you know? Look at the periodic table. Sulfur has 6 valence electrons. By picking up 2 more, it will have 8. So you have 3 and 2. We do the Criss-Cross trick. The formula for aluminum sulfide is Al2S3. Aluminum, by giving up the 2 aluminum, by giving up 3 electrons apiece, is 6 electrons. Sulfur, with its 3 sulfur wanting 2 electrons apiece, will pick up those 6. It's called electrical neutrality. There can't be a net left over or excess of electrons. Whatever electrons one atom gives up have to be picked up by the other atoms. And then we have something called electrical neutrality. Aluminum here is +3 apiece. That'll be +6 for the 2. Sulfur is -2 apiece, but there's 3 of them. That's -6. The +6 and the -6 cancel each other. That's electrical neutrality. And that's how you write the formula for these compounds, just based on their charge. Here we have sodium and iodine. Iodine is in the 7A family. It wants to be a -1. Sodium is in the 1A family. It's going to be +1. The formula is NaI. Okay. Sodium and oxygen. Sodium is in the 1A family. It's +1. Oxygen is in the 6A family. It's -2. So when you write the formula, again, the Criss-Cross trick, 2 sodiums, 1 oxygen, Na2O. That's what I mean by the Criss-Cross trick. Here you see the Criss-Cross. The 2 is the subscript for aluminum. The 3 is the subscript for sulfur. And that's the simplest way. There's one more caveat to that. You got to make sure that's the lowest ratio by which these atoms exist. Okay. Because for example, if I had nitrogen here for sulfur, nitrogen is -3. How do you know nitrogen's -3? We saw that from this example right here. It wants to pick up 3 electrons. So if I have aluminum and nitrogen, aluminum is +3, nitrogen is -3. The formula for aluminum and nitrogen is not Al3N3. We need to reduce that to its lowest ratio. It's ALN, because we can reduce Al3N3 to a lower ratio in a 1-to-1 fashion. Okay, so that's how you write these formulas for ionic compound. Here's what I mean by aluminum and nitrogen. Aluminum's +3, nitrogen's -3. The molecular compound will always break apart when you form compounds. It'll break up to their individual atoms. And so what we get is not Al3N3, we just have ALN. We just have ALN. Okay, and here are more examples. The hard ones for you guys are these polyatomic ions, because you not only need to remember the formula, you also need to remember the charge. But generally your exams are open book, so just get a good list somewhere. Okay, so chemical formula summary, the electrons are transferred, you get ionic compounds. And you want to make sure that when they are transferred, the formula that you write satisfies the octet rule. That is, the electrons that the atom will pick up will be such that the outermost shell now has 8, either by getting rid of electrons or accepting electrons. Okay, compounds are always electrically neutral, meaning that there is no net account for electrons. It can't be -1 or +1. If they are -1 or +1, then we call them polyatomic ions or ions. If it's a compound, it's electrically neutral. Okay. Ionic substances will dissociate in water to their ions. That is, if you put sodium chloride in water, it actually breaks up into sodium ions, Na+, and chloride ions, Cl-. Here's a list of polyatomic ions. There's a more extensive list in your book. Here's a more extensive list. Okay. Now pay attention to these because these are important. These formulas have these charge. This chemical right here, azide, that's not nitrogen, that's N3. And that charge is not -3, it's -1. So these are known ions with a certain amount of charge. Okay. Oxy ions are one in which oxygen is with a nonmetal. SO3 is called a sulfite ion. CO3 is called a carbonate ion. PO4 is called a phosphate ion. Get a good list because when you write formulas, a lot of these formulas come from these ions that come together. Okay. We're not looking at just an element and another element coming together. We're looking at an element combining with a polyatomic ion. A polyatomic ion acts as one element. It doesn't break apart. It exists as one entity. So you need to not only know the formula, but you also need to know the charge. Get yourself a good list, okay? Because you don't have to memorize it. You just need to know how to use it. Okay, so that's that. Look at the bicarbonate and the bisulfate. The bi, when you put a bicarbonate, it comes from carbonate, but it's a misleading because when you hear the word bi, you might think there's 2 carbonates. No, that's not the case. Okay. For some reason, we like to confuse beginning students. Okay. So when you see the name bicarbonate, it simply means that this carbonate ion, CO3 - 2, now picks up a hydrogen right here. So by putting a hydrogen on this carbonate, it's not called hydrogen carbonate anymore. It's called bicarbonate. It's also called hydrogen carbonate, but the common name is bicarbonate. Take a look at the sulfate. Sulfate is SO4 - 2. If you put a hydrogen in front of that, it becomes a bisulfate. I know it's weird, but we like to hurt beginning chemistry students, so we come up with these weird rules. Okay, so get yourself a good list and just remember that that's the name of these ions. The name of these ions. So here are common ions. OH is hydroxide. Cn- is cyanide. NO3 -1 is nitrate. CO3 -2 is carbonate. These are just groups of atoms that are clustered together and somewhat stable, but they're stable because they've gained electrons. Hydroxide has gained 1 electron. Chromate has gained 2 electrons. Phosphate has gained 3 electrons. Why did they gain electrons? In order to satisfy the octet rule for all the elements in phosphate. When you satisfy the octet rule, then you need 3 more electrons to do that. So when you have these names, know the name, the formula, and the charge. Okay? That means get yourself a good list. That means get yourself a good list. Chlorate, the chlorate ions, perchlorate, chlorate, chloride, hypochlorite, sulfate, sulfate, sulfite. What makes these things different? the charge are all the same for these. This is a good chart. Let's take a look at the chlorine oxy ions. These are called oxy ions because they have oxygen and a second element, chlorine in this particular case. But ClO4 is called perchlorate. ClO3 is chlorate. ClO2 is chlorite. ClO minus is hypochlorite. Don't bother memorizing this, just know this list, okay? Get this list somewhere. They're all -1. The difference between these are the number of oxygen. One has 4, one has 3, one has 2, and one has 1. Same thing with the bromate, perbromate, bromite, hypobromite. There's 4 series. For the sulfur, there's only 2, sulfate and sulfite. For the phosphorus, there's only 2, phosphate and phosphite. For the carbon, there's no such thing as carbonite. There's only 1. So this is a good list of knowing polyatomic ions, oxy ions in this case. Now, this is just something to help you remember these oxy ions. This is called the Mississippi rule, okay? This set of elements here looks like the state of Mississippi, and they all have 4 oxygens. These are -3, and you know that because nitrogen needs 3 more electrons. So these polyatomic has 3 more electrons. These are -2. You know that because oxygen needs 2 more electrons. So these are 2 more electrons, but they're all co-8s. This is phosphate, this is sulfate, this is selenate. And then these right here are also 8 ending, but this is chlorate, bromate, iodate. But notice these are -1. Okay, so rather than try and memorize these things, just get yourself a good list. This just gives you a mnemonic way. If we were in lecture, you would need to memorize this, but of course we're not in lecture. You guys are learning this at home. So what I want to do is just cut to the chase. Just remember these right here, okay? Because that's what you're going to be using in naming these things. Here are other lists, and notice the ending. If you have yourself a good list, then there's no problem there. So let me go ahead and talk to you about how you name these things, okay? There's 3 types, type 1, type 2, and type 3. Type 1, type 2, and type 3. Type 1 and type 2 are ionic compounds. Type 3 are covalent. What do I mean by ionic compounds? What I mean by ionic compounds is that the element is going to give up its electron and transfer its electrons. So these compounds are formed by the ions coming together. Okay, a metal and a non-metal. These are ionic compounds. What do I mean by covalent? Covalents are 2 nonmetals that want to share electrons. Okay, so the reason why we classify it as type 1, type 2, and type 3 is because that's the rules that you guys are going to use to name these things. Okay, the type 1 rules, the type 2 rules, and the type 3 rules. Remember that when compounds form, they need to be electrically neutral. That is, the positive and the negative have to combine so that when you have the compound, the positive equals the negative. When they're electrically neutral, you have a stable compound. If it's not electrically neutral, then you don't have a stable compound, you have an ion. We want compounds. We want compounds. So this is just a reminder. So let's take a look at type 1. Type 1, you have a metal and a non-metal. And how do you know which elements are metal? You know which elements are metal because if you take a look at the periodic table, to the left of boron, silicon, arsenic, tellurium, right here, this diagonal right here is the border between the metals to the left and the non-metals. Okay, that's the border. So when you have an ionic compound, you basically have a metal, an element to the left of that border, and a non-metal, an element to the right of that border. And that's because Ionic compounds means you form ions. You form ions because electrons is transferred. When electrons are given up, you have more protons than electrons. It's a cation. When electrons is picked up, you have more electrons than protons. It's an anion. And then the opposite are attracted to each other. And so you have an ionic compound. So that's what I mean by that right there. Okay, let's continue with this. So type 1, metal, non-metal, it's ionic. Metals want to give up electrons, non-metal wants to gain electrons. Type 2, this is a little bit like type 1. You have a metal and a non-metal, but now the metals come from the transition metals. Remember these elements right here? I told you that they can give up 1, 2, 3, 4. You don't know how many. Well, we need a special way to determine how many electrons they give up. So we do that by indicating how many electrons are given up. That's called the oxidation state. That's called the oxidation state. The oxidation state, like iron 2 or lead 4, okay? It tells you how many electrons that element gave up in order to form the compound, in order to form that ion. So if I say iron 2, that means it gave up 2 electrons, because iron 2 means it's iron plus 2. Plus 2 means that there are 2 more protons than electrons. That means it gave up 2 electrons. Lead 4. Lead 4 means that there's now 4 more protons than electrons. That means it gave up 4 electrons. Okay, and you state that in the name. You have to state how many electrons is released by that metal in order to satisfy the octet rule. And then moleculars like carbon dioxide. Carbon and oxygen are non-metal. So how do you determine the formula? You have to give it a prefix. Carbon di means 2, oxide means oxygen, so it's carbon, and 2 oxygen, CO2. Okay, so you first give the first non-metal a prefix and the second non-metal a prefix. So dihydrogen dioxide, the di in hydrogen means 2 hydrogens. The di in oxygen means 2 oxygens, so the formula is H2O2. Okay, that's for compounds that don't have metals. That's for compounds that don't have metals. Here are examples of type 1. The metals in type 1 have fixed charge. That's the one in yellow. That's the one in yellow right here. Lithium will always be +1. It's never +2. Aluminum will always be +3. It's never +2 or +4. Unlike iron, iron here in the middle can be +2 or +3. Okay, so we have type 1 compounds because their charge is always fixed. The charge is always fixed. It never wavers. It never wavers. Calcium is always +2, aluminum is always +3. And that's the yellow in that periodic table I showed you. Here, it wavers. Copper could be +1 or could be +2. Chromium could be +2 or +4. How do you know? You know because of the formula that you write down, okay? And then don't worry about covalent compounds. You don't have to worry about charge. There is none, okay? All you need to worry about is how many of the first non-metal, how many of the second non-metal. Like dihydrogen dioxide, that's H2O2. The name tells you the numbers. So again, this is the periodic table, and look at the charge in the bottom of these. These have fixed charge. The ones in yellow and the ones in pink, they have fixed charge. The ones in avocado or like blue-green here, they don't have fixed charge. It depends on what they're bonded to. Okay, these have fixed charge. These do not have fixed charge. It can vary. Okay, and what we're going to do is I'm going to introduce you to the 3 types of compounds. And you could just follow this flow chart because there are certain rules that you need, but it starts with the metal. Show me the metal. if the metal is group 1, group 2, aluminum, zinc, cadmium, silver, or ammonium. Ammonium, I know is not a metal, but it's a polyatomic ion that has a fixed charge. Okay, and all those elements, group 1, group 2, zinc, cadmium, silver, are the ones in yellow, right here. They have fixed charge. They don't waver. Okay, so you know what, how many electrons it's going to give up. You use that to determine how to name these things. Zinc will always be +2, cadmium will always be +2, silver will always be +1, lithium will always be +1, magnesium will always be +2. You know that. If you know that, then all you've got to do when you name these things is name the metal: sodium, zinc, silver, and then the non-metal, whatever it's bonded to. If you have zinc and oxygen, then that would just be zinc oxide. Okay. If you have sodium and nitrogen, then that would just be nitrogen nitride. If you have zinc and nitrogen, it would just be zinc nitride. You just name the metal and the non-metal. That's the key. Okay. On the other hand, if you have elements, metals that do not have fixed charge, and what elements are those? Are the ones that were in avocado green or turquoise blue. Okay, then you have to name the metal, its oxidation state, how many electrons it gave up, and then the non-metal. That's the rule. Okay, and then if you don't have any metals at all, then you just name the first element non-metal and the second element non-metal, but then you indicate how many by the prefix, like H2O2. You guys know that as hydrogen peroxide, H2O2. The correct name would be dihydrogen dioxide. Okay, dihydrogen dioxide. How about something like water, H2O, dihydrogen for the 2 hydrogen, monoxide, 1 oxygen, dihydrogen monoxide. So we name the compounds that don't have metal by this format: a prefix non-metal 1, a prefix non-metal 2. Okay, and then if you have a hydrogen in front of that formula, then it's an acid, like HCl, that's hydrochloric acid, or H2SO4, that's sulfuric acid. Okay, but let's take a look at the rules. For type 1, you have a metal and non-metal. Suppose you have aluminum and oxygen. Okay, it still needs to be electrically neutral, but that name is just aluminum oxide. If you have silver and sulfur, then that name is just silver sulfide. You always give the second element an IDE ending, indicating it's the anion. You give it an IDE ending. Let's take a look at polyatomic ions. NO3 is a polyatomic ions. That's cadmium nitrate. Ammonium sulfate. Okay. You don't put numbers in these things like in the second one. You just name the cation and the anion. Look at the second type of ionic compound, ones in which the metal can give up 2, 3, or 4 electrons. You don't know, so you have to state it in the name. And the way you name these things is you name the cation first, okay, followed by its oxidation state. Its oxidation state is how many electrons it gave up, followed by the anion. So you see how I name aluminum here first and then oxygen, but gave oxygen an oxide ending? Well, the elements here, aluminum is always +3. It never wavers. But in this second example, iron could be +3 or +2. So the audience needs to know. So when you write the name, you indicate what the charge is. Iron 3, that means it's Fe +3, and then chloride. Okay, so the element that makes this right here, if you read iron 3 chloride, it's Fe with a +3 charge, and then Cl minus, because chlorine is a -1 charge. And then when you write the formula, you do that crisscross trick I showed you. You need 3 chlorines to match the +3 iron. And so the formula would be FeCl3. Okay, but that's the key here, is that you need a Roman numeral to indicate how many electrons your cation has. In this particular case, the iron is a +3. In this particular case, the lead is the +4. Here, the tin, Sn, is a +2. The gold is a +1. Okay, this second row here is a polyatomic ion. This first is elemental. So these are examples of naming. Let's take a look at the third one. For the last one, it's pretty easy. You just give the prefix, how many, the non-metal one, the prefix, how many, and non-metal two. Like for example, oops, sorry. This right here, P2O5, it's phosphorus and oxygen. There's 2 phosphorus, so you say diphosphorus. And then there's 5 oxygen. So the prefix for 5 is penta, but you don't say pentaoxygen, you say pentaoxide. The second element always has to end in an IDE if it's an elemental ion. Diphosphorus pentaoxide in this particular case, okay? Look at sulfur trioxide. Sulfur trioxide, 1 sulfur, 3 oxygens. So type 3 are pretty easy to name because all you do is name the elements. They're non-metals, and you give it a prefix to indicate how many. Okay. So this is generally just an exercise of asking you which of these are type 1, which of these are type 2, and which of these are type 3. Remember, type 1 have metals in which the metals have a fixed charge. And which ones are those? These have metals with fixed charge, the ones in yellow. Type 2 are metals with not fixed charge, these are right here. And then type 3, these are elements in which there are no metals. There are no metals, okay? So if you take a look at the first one, magnesium, and ClO3 is chlorate, okay, chlorate, then that means that this is a type 1 compound. Why? Because magnesium has a fixed charge. Copper, the second one here, oops, sorry, second one here, that's copper and bromine. Well, copper has a variable charge. So you would say copper, whatever that charge is, and then bromide. So that's what I would be talking to you guys about if we were in class. Determine if the element is elemental or polyatomic. If the compound is a type 1, type 2, type 3, or an acid. So let's go back and let's see this first one. This is a type 1. Why? Because magnesium has a fixed charge. HClO, that's an acid. N2O4, that's a type 3 because there are no metals. NH4NO2, that's a type 3 because NH4 is considered as a non-metal. Na3AS, that's a type 1. Why? Because sodium has a fixed charge. V3N, that's a type 2 because there's a metal and the metal has a variable charge. So you can actually see the answers here, okay? The first one is a type 1. Well, actually, this is a group activity that I would generally have the class do. Here's the answers, okay? First one's a type 1. Number 4 here means it's an acid. 3 is a type 3. 4 is an acid. 3 is a type 3. 2 is a type 2. So you can just look at the legend down here to practice that. Now, the last, I know I'm running a little bit late. I just want to do some practice and then we'll be done. Okay. So let me go ahead and just make sure that I have everyone here. Let's practice some of these things. Okay, let's practice some of these things. Yes, this is what you guys will be doing in the crossword assignment. The crossword assignment is generally writing the name or writing the formula. It's giving you practice in terms of a game. Okay, so that was the question that was posed. So you guys can certainly hopefully see that. So let's take a look at this. SRSE. The way you want to approach this is look at the first element, SR. SR is in group 2. Group 2 elements have a fixed charge. That means strontium, SR, is a +2 charge. Se is selenium. Selenium wants to give up 2 electrons. So in this particular case, the formula for this would be, or the name of this would be strontium selenide. Selenium, drop the ending and put an IDE. So that's what we have right here. Oops, what's going on? Strontium selenide. See how I'm not saying it's selenium. I drop the ending and put IDE. Okay, the next one. This is also type 1. Magnesium has a fixed charge. It's +2. This is just magnesium nitride. Name the first element, name the second element, put an IDE on the second element, magnesium nitride. This next one, again, it's a type 1. Why is it a type 1? Because the metal there, the lithium, has a fixed charge. It's always +1. So this name would be lithium oxide. Lithium oxide. Okay. Now let's take a look at this one right here. These are polyatomic ions. You should know SO4 sulfate. This is just strontium sulfate. Get yourself a good list of the polyatomic ions. The SO4 is called a sulfate. Don't change the suffix. It's sulfate, strontium sulfate. Magnesium phosphate. PO4 is phosphate. Magnesium phosphate. And then finally, ClO4 is perchlorate. Get yourself a good list. That's just lithium perchlorate. So when you have these types of compound, type 1, you don't put Roman numeral because you know the charge, and you just name the cation and the anion. Here we have the name. We want to come up with the formula. It's potassium sulfide. You know the symbol for potassium is K. You know the symbol for sulfur is S. That's what you start with. Then look in the periodic table. Sulfur is in the 1A family. It's going to be +1. Sulfur is in the 6A family. It's +6. Okay. But because it's in the 6, it wants 2 electrons. So it's -2. How do I know that? Look over here. Okay. Sulfur is -2. Why? Because it's got 6 valence electrons. It needs 2 more to get 8. It needs -2 electrons. Phosphorus, it's got 5 valence electrons. It needs 3 more to get 8. It's a -3. So the numbers in the bottom of these symbols are how many electrons it needs. That's the charge. Aluminum +3, phosphorus -3. And then if it doesn't have a number here, it varies. It varies. So let's go back to where we left off. This potassium and sulfur. We know potassium is +1, sulfur is -2. We do the crisscross. The 2 on sulfur is now the 2 in potassium. The 1 in potassium, that's K, is the 1 in sulfur, and that becomes the subscript. It's called the crisscross trick. So the formula is K2S. Let's take a look at the next one. Cadmium and bisulfite. Bisulfite is HSO3. You have to find that in a list of polyatomic ion. What are the charge? Cadmium's +2. Bisulfite is -1. We do the crisscross. The 1 in bisulfite is the 1 in cadmium. The 2 in the cadmium is the 2 in the bisulfite. These becomes the subscript. we have the formula CdHSO3. When we do that, crisscross, it's electrically neutral. The cadmium in this final formula is +2. The bisulfite in this final formula is 1 negative apiece, but because there are 2 of them, that's -2 net, it's electrically neutral. Let's take a look at another one, okay? Let's take a look at this one, manganese. This is a type 2. Type 2 means that the charge varies. So you have to indicate it with a Roman numeral right here. We have manganese and nitrogen. Manganese and nitrogen, okay? So the way we would do this is we would say crisscross. We put the 2 in the manganese, the 3 on the nitrogen, crisscross. That means that the oxidation state of the manganese, because remember, there's the way we name this is the metal, the oxidation state, followed by the non-metal. So now we know that the name is going to be manganese 2 nitride. We have to figure out what the charge of the manganese is, and so we do a reverse crisscross. Let's take a look at this right here. What's the name of this? Manganese and nitride. You start with manganese, and there's 2 nitrides. There's 2 nitrides. The manganese, if you do crisscross, there's 2 manganese and 1 nitride. That means that the manganese is a +2. So you would name this as manganese 2 nitride. Okay. Let's take a look at this next one. So I actually go through each scenario. Let's take a look at this iron 2 sulfide. The symbol for iron is Fe. The symbol for sulfur is S. We know that the iron, according to that name, is +2. We know the sulfur, according to the periodic table, is -2. We do a crisscross. So we write the formula as Fe2S2, but we can reduce that to a lower ratio. The formula is FeS. If you can reduce the coefficient, that's the number that's in the bottom, to a lower ratio and not a fraction, then do so. Let's take a look at tin sulfide. Tin is Sn, but it's a +4 in this case. Sulfide is SO3. So that's what we have. We know that tin is +4. How do you know? It's in the name. You know that sulfide is -2. How do you know? Look it up. Look it up. Sulfide is -2. We do crisscross. The 2 becomes with the tin. The 4 comes with the sulfide. That's the formula. Sn2, SO3 parentheses 4. When you have a polyatomic ions and there's more than one, you have to put a parentheses around it. This can be reduced to a lower ratio. 1, if you divide by 2 and by both, you have Sn parentheses SO3 2. If you can reduce it to a lower ratio, you need to do so. Okay. Let's take a look at this one right here. This is the type 3. Notice there are no metals here. No metals. So the way we name these things is first name the first element, the second element, and we give the number in terms of a prefix. This one's nitrogen and oxygen. So it's dinitrogen, dioxide, not dihydrogen, dinitrogen, dioxygen. It's dinitrogen dioxide. That's what you see right here. 2 nitrogens, 2 oxygens, dinitrogen dioxide. Second element always has an IDE ending. That's the name. Look at this right here. Again, non-metals, xenon and fluoride. So 1 xenon, 2 fluorine, you never put a mono on the first element. Never put a mono on the first element. This is just, you notice I will drop it. It's just xenon difluoride. This right, the next one is 4 phosphorus, 10 selenium. Okay, so 4 is tetra, 10 is deca, tetraphosphorus decaselenide, and that's the final name. Okay, this is a type 3. How do you know it's a type 3? There are no metals. Nitrogen is not a metal, xenon is not a metal, phosphorus is not a metal, selenium is not a metal. When you don't see a metal in the formula, you have to use the type 3 nomenclature. Okay, let's take a look at this right here. What's the formula of diboron trisulfide? It's easy, 2 borons and 3 sulfur. The name tells you the formula. Silicon tricarbide. Silicon tricarbide means SiC3. Like that. Iodine monochloride. Notice I put a mono on the second element, but not a mono on the first. Always a mono on the second, never on the first. So this is ICL. Okay. So that's, these are more examples from that to practice, but that's basically what this first section is about, is naming these things and be comfortable with naming, because you will need that when you do stoichiometry. Sometimes I don't give you the formula. Sometimes I just give you the name. You have to come up with the formula. Okay. So that's basically what this discussion is about. The next discussion next week, we'll be taking these formulas and writing the structural configuration, the geometry. Is it flat? Is it like a trigonoplanar? Is it tetrahedral? That's what we're going to be doing next week. But naming is pretty intense. So that's why I just wanted to cover it here in this discussion, and at least give you a bird's eye view. Okay, so what you need to do is practice, and the crossword puzzle that you have there will give you some practice in doing these things, and that's extra credit. Okay, but that's all I really wanted to say about this. It took longer than usual, and that's because you guys are not in the class, and I really wanted to make sure that you understand the fundamentals. But it doesn't look like there's any questions in the chat, but if you do have a question, just fire me a question in Canvas. I'll be sure to get to it. And hopefully I will get the recording of this and post it.